And I will tell you something about graph isomorphism problem and asymmetric graphs and partial symmetries. So this is going to be just a part of what I deal with in my PhD. And all of these topics deal with partial automorphisms of graphs. And I chose for you just some part of it. So I'm going to tell you something more about the part that deals with partial automorphisms and graph isomorphism problem and partial automorphisms and asymmetric graphs. And these are all new terms, so we will go through them and define them. Okay, so this is just like what I'm going to talk about in this talk. So we define two graphs are isomorphic if there is a bijection from one graph to the second graph that will preserve adjacency of vertices. So what do I mean? It means that if there are two vertices which are adjacent in one graph, they have to be also adjacent also after the bijection, right? In the image of the bijection. So, and then there is this graph isomorphism problem, which asks you to decide whether two graphs are isomorphic. And so let's have a small example. So these two graphs have 6 vertices, and you should tell me whether they are the same, okay? Structurally the same, isomorphic. So, probably yes. That's the correct question, answer. But how do we show that, right? It's non-trivial even for small cases for humans to decide something like that, right? So one way to do that would be to differentiate two groups of vertices. And as you can see in the first group, these 3 vertices are not connected among themselves. The same holds for these blue ones, right? They are not connected to each other. And the same holds for the red ones. And so it turns out that there is a bijection that will map blue ones to blue ones and red ones to red ones. Okay? And as you can see, this is not really trivial for humans to do that, but computers are fast, so that's good. And the practical motivation for graph isomorphism problem comes from what I heard from chemical databases, right? So let's say you have a big chemical database of molecules, which are basically graphs, right? Each molecule can be encoded as some mathematical graph. And here comes a new molecule, and you are to decide whether you already have it in your database, right? Because you do not want to duplicate data, and it would be, you do not want to do that. So is it in, right? And this is just a graph isomorphism problem, really. And also, another motivation to study this problem also comes from graph neural networks. So as it turns out, expressivity of graph neural networks really boils down to deciding graph isomorphism via Weisfeld lemma, right? So the graph neural networks and their expressivity, how they can differentiate between two graphs, comes down to deciding Weisfeld lemma algorithm, which is the fastest algorithm for graph isomorphism. Okay, so the people who are neural networks, you might maybe say something more about this. This is just motivation for me. And so what is the symmetry of a graph? Okay, right now we are basically talking about isomorphism. Right now we want to tell something more about automorphisms. Okay, so if you have this simple graph here on the left, which is just a triangle, it has 6 symmetries, right? This is the trivial one. You just map every vertex to itself. And then you have like reflection on this axis, reflection on this axis, and some rotations. Okay, so it has in total 6 symmetries. And we define automorphism as an isomorphism from a graph to itself. And then we have come now to understand also asymmetric graphs. And asymmetric graph is a graph which has only trivial automorphism, okay? Trivial one. So it has only such a bijection that will map everything to itself, okay? So this is called asymmetric graph, and this is the smallest asymmetric graph. So as you can see, there is no axis of rotation, and you cannot also make any reflection. And then there is this famous problem of graph asymmetry problem. So you have on the input you have a graph, any graph, and you are to decide whether it's asymmetric or it's symmetric. Okay? And another related problem is asymmetric graph isomorphism problem. So you have two asymmetric graphs on the input. So you know that they are asymmetric. And you are to decide whether they are actually the same asymmetric graphs. Okay. So let's talk about the zoo. And I don't mean this zoo. I mean this zoo, which is much more complex, I would say. It's complexity classes zoo. And so we do not know whether graph isomorphism problem is in P or it is NP complete. And it is one of the biggest open questions in theoretical computer science, I would say. And but we know that there are some problems which are reducible to each other between graph isomorphism and other problems. And for instance, if we take this graph asymmetry problem, we know how to reduce it to graph isomorphism problem. Okay? We also we know that if we can we can also reduce graph isomorphism for asymmetric graphs to graph isomorphism. Okay, that's easy to see. But it turns out that for these two problems, the other direction is not clear. Okay, and this is also open. These are open questions. So we do not know how to reduce graph isomorphism problem and some other problems which are related to graph asymmetry problem and graph isomorphism for asymmetric graphs. Okay, and we would like to know more about this beast, which is graph isomorphism and how it's related to other beasts. And so in one part, which I'm not going to tell you about right now, we have defined like several decision problems which are related to both, and we hope to somehow get new insights into this direction which is not clear. Okay, this is maybe for another seminar, and just yeah. But it turns out that for tournaments, these are directed graphs with exactly one edge between each two vertices. Okay, so it is a complete graph, but it has directed edges among the vertices. Okay, and it turns out that graph asymmetry problem is a polynomial time randomized reduction. I'm not going to explain that. It's equivalent to deciding tournament isomorphism problem. Okay, and this was proven by Schweitzer, who is maybe like Ilya Sutskever for AI. This guy is for algebraic graph theory and stuff related to graph isomorphism problem. So for these graphs, tournament isomorphism problem and tournament asymmetry problem is equivalent in this sense. So for tournaments, this is solved. But we do not know for general graphs. Okay? So now we come to asymmetric graphs, and as you can see, we want to somehow understand them more to better understand this relation and possibly the reduction. And by the result of Erdős and Renyi, Erdős is like Hinton for AI. Okay, I'm trying to make some analogies so that we find common ground. All right. So almost all graphs are asymmetric, but it turns out that almost all regular graphs are also asymmetric. And the regular graph is just, I'm going to write it here. Oh, okay, technology works. Okay, so this is a regular graph. It means that from every vertex you have the same number of outgoing edges. Okay, so it turns out that if you choose randomly from the regular graphs, which look like this, and they have, the same number of neighbors from each vertex, it turns out that almost surely you will get also asymmetric graphs, which is somehow, I would say, not expected. And if we just compare ratio of asymmetric graphs to the number of all graphs on the n vertices, like this ratio grows quickly to 1, right? It tends to 1 very quickly, so almost all graphs are asymmetric, and we would like to study them more, right? Because usually people tend to spend more time with symmetries. We want to understand asymmetries in this case. And they are also important for the following reason, as it turns out that practical graph isomorphism solvers, asymmetric graphs are really hard for the practical ones as well. Okay, so this was again by Pascal Schweitzer. I've stolen it from his slides. And these are the 5 best graph isomorphism tools And as you can see, like this is number of vertices. This is the time it takes to decide graph isomorphism for these graphs. And so it turns out that there are cases where deciding isomorphism problem for graphs which are asymmetric is hard. So let's revisit what we mean by symmetry. And I want to give you again this very simple graph. But right now I want to challenge your maybe intuition a little bit. So this is, it has 6 permutations, right? That preserve the symmetries, 6 symmetries. And I'm going to iteratively construct Sierpinski triangle out of it. Okay, so I divide the midpoints and I connect them. Okay, so this is the first iteration. This is again, I take these smaller triangles, I again take their midpoints and I connect them and I arrive at, third iteration, which is this graph. And so I think that each of you would agree with me that this graph is intuitively more symmetric than the first copy, right? It has more like self-similarity on different levels, right? It has induced subgraphs which are similar. It has not only like this global, rotational symmetry and reflections, but you see like these small copies of triangles which are also symmetric among themselves. And we call that local symmetry. And this is just, let's say, intuition for my future slides. So for that reason, we define partial automorphism of a graph. And it is an isomorphism between 2 induced subgraphs of that graph. And okay, so what do I mean? Let's take some simple example. This graph, 7 vertices. I take induced subgraphs on 3 vertices, for instance, this one and this one. And as you can see, they are isomorphic, right? They are the same. Okay, so this is valid partial automorphism of that gamma. Okay, but also, as you can see, there is this the same induced subgraph, but it has also this reflection, so it's also valid partial automorphism. Okay. And so, okay, so I told you about this intuition behind fractal graphs for those. At ICM 2011, which is a big conference for these problems, Babai, who is again one of the big names, okay, argued that solving graph isomorphism problem will involve looking at local structures and so possibly at partial automorphisms, okay. And also the fastest known algorithm for a graph isomorphism problem, which is Weisfeld-Lehmann, okay, black box, but it's fast. It's based on the idea of local symmetries and aggregating local information, okay. So we want to study how asymmetric graphs are from the perspective of partial automorphisms. And so we define a measure how to do that. But before that, I would like to tell you that if you take the set of all partial automorphisms and under composition, it will form an inverse monoid, which is again some concept which I'm not going to explain. The important fact is that these partial automorphisms can be related and composed, and they will give you a structure, okay, also. And it was fully characterized, this for inverse monoids for graphs, partial automorphism inverse monoids. But it turns out that it's very hard to compute, right? Because you have to compute several orders of isomorphisms, right? You have to compute the isomorphism among each pairs of induced subgraphs of that order. So there is a lot of computation, and we would like to somehow avoid that. This is how it can be done if you encode each graph with its canonical hash, and then you store them in a hash set and compare them in the hash set. So it's hard, okay? And already this canonical function, it's a quasi-polynomial by the result of Babai. So it's hard even for very small graphs to compute this. But we would like to understand something, right? And so for that reason, we define asymmetric depth, which will be a measure of asymmetry. And it has to deal with partial automorphisms and their order, okay? So a rank of partial automorphism is the order of induced subgraph in its domain. And it's trivial to see that every non-trivial graph has some non-trivial partial automorphism. So for that reason, we see that there must be some which is the largest, okay? Which has the maximum rank, okay? The largest non-trivial partial automorphism. And so we define the measure of asymmetric depth of a graph on n vertices as this d is the asymmetric depth. So this is the order of the graph minus the largest partial automorphism, minus the rank of the largest partial automorphism. All right, so example. This is graph on 6 vertices, and its largest partial automorphism has rank 5. It is this one, okay? It's a reflection, and it takes these 2 vertices, and this, it's not defined on this vertex, okay? So this is out, and as you can see, there is a reflection. And so it has its accompanying asymmetric depth is equal to 1. Okay, this is a bigger beast, and the only thing that somehow restricts the symmetry is this red edge, okay? So we would like to somehow avoid that, and it turns out that you need to take out these 3 vertices out of the induced subgraph. This one, this one, this one, okay? And this one will be deleted along with them, so there will be non-trivial partial automorphism of rank 25, and so its depth is equal to 3. Okay, so have we helped ourselves? Yes, a little bit, but as you can see, there is still this sum, there is almost everything is the same. We would like to bound this asymmetric depth, okay, to somehow get better time complexity out of it. So, yeah, the question is there an upper bound for asymmetric depth? And then we would like to find some, examples of graphs. And we would like to also mention some relationship between different measures of symmetry, because there are more of them. All right, so as it turns out, there were a series of upper bounds. This was the last one before me. This is the author here. So this is 2/3 of the order of the graph, okay? And so we were able to improve it to n minus 1 divided by 2, okay? But these ones are also valid upper bounds. So just a short idea of how to do that. The idea is to define a very simple partial automorphism on any graph that will swap just 2 vertices, okay? It will be very trivial symmetry in a sense. So for any 2 vertices, this is just some graph, okay, for illustration. These are the 2 vertices. I would like to somehow define a partial automorphism that will just switch them, okay? And so this is the trivial that every 2 vertices have some common neighbors and some neighbors which are only to one of them, okay? This is the symmetric difference of these 2 vertices. And so it's easy to define it for any pairs of vertices. You just fix everything that is outside of symmetry difference, and you swap those 2 vertices, okay? And so for any 2 pairs of vertices, you will get this bound. All right, so then you just want to take the minimum over all pairs of vertices, right? Because that would be the highest upper bound that you can get out of this method. And this can be bounded above by average, and you can work with average, and after some computations, you will arrive at this upper bound. All right, so then we want to answer the question whether there exists some graphs for any value of asymmetric depth, okay? And we would like to find a graph that has this for any 2 pairs of vertices, okay? This would be our best record graph. If we can find this, we know that our upper bound is very good, okay? And as it turns out, possible candidates would have to have these parameters for strongly regular graphs, which is a class of graphs for now, okay? And the question really boils down whether there is an asymmetric, strongly regular graph with those parameters. And as it turns out, there are such graphs. There are many of them. The problem seems to be to check whether they have this asymmetric depth, okay? Because the time complexity scales very fast. So we checked all graphs from the database with more than 37 vertices, no success. But then there are 124 candidates on 37 vertices. And if one of them at least has this asymmetric depth equal to 18, it would be success. And each of them has asymmetric depth bigger than 10. I checked that. But then there is this gap, okay? I have to somehow make my computations better. All right, so I'm going to skip that. The first problem is that if you really want to check whether the graph has asymmetric depth equal to 17, you have that many induced subgraphs that you need to compute their canonical hashes, and then also check whether there is some copy of canonical hash, okay? And each canonical hash takes this amount of time to compute, and roughly for one graph, it takes 6 days, okay? And I have 124 of them, right? So 2 years, I mean, I want to be out of this school out of 2 years, right? So, so I want to check them in parallel, but okay, the problem too is that each canonical hash takes 64 bits, and this cannot be reduced. So if you again compute this, you will get that you will need at least 120 gigabytes of RAM if you want to be fast, right? Because if you store it on the SSD, right, you are getting some overhead there. But you are quite lucky because canonical hashes on average share 20 bits in prefixes. So you can use 3A data structure, which is, you reduce it to 66 gigabytes. But still 66 gigabytes, not even Jupyter here has, right? Jupyter is the departmental server. It has 64 gigabytes. So that was the reason why the server dropped. So as it turns out, I'm just going to try another idea, which is called external sorting. Maybe some of you have heard about it. Is that you will basically divide the induced subgraphs into batches. And for each of the batches, you will basically compute each of its canonical hashes. And then you will store them in separate files. And as it turns out, that then you can sort them without loading them all into memory, okay? With a similar method as merge sort. Okay, and this I hope will work, and I hope that I can use parallelism then using this. All right. So just to get some intuition, if you want to study something, right, you would like to have some kind of examples, right? If you don't have examples of your objects that you want to study, how can you study them, right? So we wanted to collect some examples of graphs which are asymmetric and have different values of asymmetric depth. And we used branch and bound techniques, and we extended small graphs to bigger graphs. And we collected the record graphs. And this is the table that shows you for each order of graph, which is n, the maximum record asymmetric depth on that order. And so as you can see, like with the order of the graph, the asymmetric depth tends to increase for the record values, okay? So then you would like to ask, okay, so can I find examples for any value of asymmetric depth, okay? And so we found a method how to generate examples. So you take h-dimensional hypergrid consisting of h-dimensional hypercubes. Okay, this is for two-dimensional case. And it has this automorphism group of symmetries. And they have the important property that this minimum of the symmetric difference over all pairs of vertices increases with the growing dimension h, okay? And so you would like to turn this into your advantage. So how to make asymmetric graph out of this one? So we will somehow attach some new things to it to make it asymmetric. So this is one way how to do it. We attach an additional hypercube on top of one of the previous ones. Okay. This is still not yet, this is already asymmetric, okay, as you can see, but this wouldn't be the case for bigger dimensions. So we have to ensure that it will be also for the other dimensions. And so we have to attach another additional hypercube, which would be basically just defined as the smallest non-trivial, this was not expected. So you would just define it as where would this red cube be after you rotate it with the smallest non-trivial rotation, okay? And so that's the place where you will place the second hypercube. Okay, and this will work for bigger dimensions. And this is the graph that you will get for 3 dimensions. Okay. Okay, these are the 2 hypercubes that were attached. This is asymmetric graph, and as it turns out, it can generate you examples of graphs which have asymmetric depth equal to minimum over symmetric difference of all neighborhoods over pairs of vertices. I should came up with some shortcut for that. And since this minimum scales linearly with the dimensionality of the hypercubes, this will give you infinite number of examples. And I validated it computationally for small dimensions, and it works. All right, so then you can take probabilistic approach and ask the following. Given any integer, and if I draw randomly a graph from the set of all graphs on n vertices, then the question is, can I find the graph? And it turns out that you can do that almost surely, okay? And so we have like several, let's say, indications that this is actually usually the case, that if you choose randomly the graph, it will be asymmetric and it will have large asymmetric depth if you let the n grow to infinity, okay? All right, so the last question would be that what is the relation between this measure of asymmetry and other measures of asymmetry? And Erdős defined this degree of asymmetry of a graph as the minimum number of edges that need to be removed from the graph so to make it symmetric, okay? Example. From this graph, you just need to delete this one edge, the red one, and it's symmetric, okay? There is, for instance, rotation, which will take this vertex to this one to this one, this one to this one, okay? All right. For the second graph, you need to take these 2 edges to make it symmetric. Okay? Then there will be this reflection along these axes, okay? If you take these 2. And this one will be fixed, okay? All right, so we have some examples. They have different values of asymmetric depth and this degree of asymmetry. And so the question is, can we somehow, see whether we can increase one parameter and fix the other one? And what is the relation between different values of parameters of these 2 different concepts of asymmetry? Okay, so these ones were computed by hand. I filled the table. That's for small examples. You can get the examples of graphs for these parameters with the method of hypergrids that I described. I think I can manage these ones, okay? If I fix D to 1 and just want to increase the number of edges that I need to remove, I think I can do it if I will have time. And I think I can do it also for these examples, but for these ones, it turns out that I don't know yet. There must be some new method developed that will be able to help me to fill the table. All right, so that's all. Thank you for your attention, and if you have any suggestions or questions, I would be happy to answer them.